My name is Devesh. I work at Shopify as a developer on their point of sale team. I primarily work on their mobile stack, the point of sale app. So started with Android, then a bit of React Native, and now currently iOS. Shopify is this online e-commerce company. Is this e-commerce company empowers merchants to sell their products. So hey, we have big merchants like Kylie Jenner, Allbirds, Um, and we are always hiring. So if you're keen to know more about Shopify, you can just ping me. Um, as such, the topic is Swift for TensorFlow. So you might be wondering, we primarily use Python for TensorFlow. So why Swift? So exactly why Swift? Uh, Now Swift, this is a blog post written by Jeremy Howard. He is one of the team members of Fast.ai, apart from his other notable achievements. He talks about how he goes into depth about how Swift as a Python alternative seems to be a foreseeable, seems to be a future that he can live in. So Swift is a general purpose, multi-paradigm compiled programming language. Too many words together. General purpose. So Swift was not built with any particular application domain in mind. You can use Swift for any application, any domain. So you're not restricted to using Swift for building iOS apps or macOS apps. You can use Swift to build server-side apps. You can use Swift to build machine learning models, like we're going to do today. It's multi-paradigm. So multi-paradigm in the sense you can you can use it in the context of functional programming, object-oriented programming, maybe meta-programming. It's compiled, so it's not interpreted like Python. So it has a compiler which will translate your source code into machine code. So Swift relies on LLVM, and Swift is fast. It's not what I claim. It's based on observations by Jeremy Howard. So as you will see, you can often get the same performance as carefully optimized C code. Swift has value semantics. So what exactly are value semantics? This is some Python code. We're defining a container, which is basically an array containing 3 elements, 1, 2, 3. Let's create container 2, which is equal to container, and now print out container and container 2. We expect both of them to have 1, 2, 3 values. Now let's go ahead and mutate, update the first value of the container array to be 10. Now if you print out container and container 2, both those values are mutated, but that doesn't make sense. You create a container 2 to just have same values as 1, 2, 3, but mutation happened. So these are the side effects of having reference semantics. So what would happen in a language, let's suppose value semantics, something like Swift. So this is some Swift code. So the container is also an array, 1, 2, 3. The container over here is preceded by a let keyword. Let essentially means this container object is immutable. So I created a container 2, which is also equal to container 1. So you can see on the right side, it's 1, 2, 3. Now, if you were to print container and container 2, 1, 2, 3, but now if you were to update container's first value to be 10, cannot assign through subscript. Container is a let constant. Basically, container is a constant. The value is set to be immutable. So you cannot go ahead and update them. So what do you do in this case? So Swift is expressive, right? So over here, you're using let, and you're letting everyone know that this is a constant, so this value cannot be mutated. So instead use a var. Var lets you create mutable instances. So here I have created a mutable instance of 1, 2, 3. I'm assigning it to container 2. I'm printing container 2, 1, 2, 3. Now container 0 is equal to 10. Now if I print container and container 2, container is 10 to 3, while container 2 is still 1, 2, 3. You see the changes in container didn't have any unintended side effects on container 2. So the value semantics preserves. You're essentially treating arrays as values, and you're using the same value to fill into a second bucket. You're not going, when you change the value in the first bucket, you don't really want the second bucket to be impacted. You don't want unintentional side effects. In the case of Python, if you wanted the same effect, you would have to use clone, and then your container 2 would be a new instance having possibly all the values of container, and you won't face the same issue. So we looked at general purpose multi-paradigm compiled programming language. We looked how Swift is first. We looked Swift supports value semantics. So Swift is safe. What do we mean by safe? It's so Swift is a strongly typed language. It's statically typed. So you have here I've declared my mutable value, which is of type int. I'm assigning it to 10. Even though Swift is statically typed and strongly typed, you could go ahead and just get rid of int. Swift compiler has this ability to infer the type from the value being assigned. So the value is of type int. Now if I go ahead and try to set the value to 20.0, what do you expect would happen? Like I already mentioned, Swift is strongly typed language. So assigning a decimal to an int is a total no-no. The compiler will warn you. In fact, the compiler is smart enough to assist you, to help you to convert it to an int. It will guide you. The compiler is your best friend out here. And Swift is a protocol-oriented language. So what are protocols? A protocol is something like this. It has a bunch of methods, no definitions. It can extend to other protocols. So over here, this is a comparable protocol taken directly from the Swift standard library. It conforms to another protocol, which is equatable. So equatable if the name does not make sense. If the name is too obvious, like the left-hand side value, right-hand side value should be equal. Comparable essentially means they can be compared. So you have these four functions: less than equal to, greater than equal to, greater than. But if you look at this, the code for all of these should be similar. So you might be wondering, what why repeat the same code through and through? When you know if it's less than, it cannot be greater than, you could just reuse the same value. So Swift has this capability to extend, so you can you can add additional capabilities to an existing type. So in this case, we are defining an extension on the comparable type. So let's say the function greater than is essentially reusing the value from less than. So it's the definite opposite. And that's it. All comparable types will get this function for free, and you don't really have to go ahead and implement this same logic all throughout. So you get maximum code reuse. And let's talk about automatic differentiation. When Google announced Swift for TensorFlow, automatic differentiation was a big thing. So what exactly is all the hype around automatic differentiation? So Andrej is a director of AI at Tesla. He wrote this awesome blog post on Software 2.0 on how languages such as C, Python, this is just Software 1.0. We need something that's 2.0. You also definitely read this. Now, Jan LeCun, he clearly stated like deep learning needs a new programming language. Somit is the co-creator of PyTorch, and he agreed Swift is a great viable choice. So what is this big hype around automatic differentiation? We'll get back to that point in a while. We'll build our own differentiation formula, differentiation mechanism. So why Swift for TensorFlow? Well, there's an entire blog post. It's huge. Probably need more than an hour to read the entirety of it. But apart from the points we already mentioned, there's some interesting use cases, how they conducted a survey, how they evaluated other languages like Rust. Why not just go ahead with Python? And all the examples in this presentation will be run on Google Colab. So there's no official Swift kernel support on any of the Jupyter notebooks, any of the Colab notebooks. So Colab is just a nice feature-rich layer over Jupyter. So you have to go to the Swift for TensorFlow repo, click on any of the tutorials, or just click on opening a blank notebook. If you go, you can verify your runtime. It's Swift, and if you want, you can even enable any hardware accelerator like GPUs or TPUs. So, well, Swift has a really good IDE on macOS called Xcode. You can debug those programs like you would do any other Swift program on Xcode. So you can literally go through your model, check what's happening, inspect values at every point. Let's consider this simple equation y equal to x squared plus 2. In Swift terms, this would just be y equal to x multiplied by x plus 2, or you could just use the square function as well, but x into x by 2. So the graph of y equal to x squared plus 2, what do we aim to achieve through this? So the gradient, the gradient is the rate of change in y coordinates over the x coordinates. So this is the most important thing you're going to need today. So the gradient is defined by the differentiation of y over x with respect to x. So in this case, our equation is x squared plus 2. Now x squared plus 2, to differentiate x squared, we can use the power rule, which simply states x raised to n with respect to x is nx raised to n minus 1. I go over here, and we're going to equate, run through a loop. So we're differentiating x squared plus x with respect to x. And so the answer is 2x raised to 2 minus 1 plus 0, because differentiation of that should have been 2, not x, so that's a mistake. So differentiation of a constant is 0. So xy plus 2. And so the answer you get is 2x. And so yeah, back to a simple Swift equation, x into x plus 2. How would you represent that mathematical expression in Swift? You just define a function. And so the way you define a function in Swift is by using the keyword func, giving a name to the function. In this case, we'll just call it the magical formula, supplying the argument you need, so x, which is of type float, and the return type of this function, which is float, preceded by the arrow key. And the return value that we plan to specify, so this is a simple equation, x into x plus 2. Well, when you're browsing online, you might notice the secondary syntax for functions. So what changed over here? You have an underscore that is preceding the x. So what changes is when you're calling this function, you can just call magical formula and supply the value. You don't supply the named argument. So in the case where there is no x, when there's no underscore preceding the x, you do have to supply the named argument, that is x in this case. So magical formula x colon 3. There's one more thing. Swift wants to make your life easier. So if there's a single line expression, you can even get rid of return. And we want to let a compiler know that this function is differentiable. So how do you make a function differentiable? By just using the attribute differentiable. And this just states that the equation x into x plus 2 is differentiable, and you have compile time checks for it. So let's calculate the gradient, dy by dx. At what point? I just chose a random point, let's say 3. In the magical formula that we just built, and we store it in a result, which is let, because it's immutable, and let's see the value. So 2x, which is 6.0. Let me show you alternative syntaxes to using the gradient function. What happened to our magical formula over here? You could, instead of using a function, you could just apply a closure. So the closure syntax is the parameter and followed by an arrow and the return type and in and a bunch of statements. So in our case, X, we didn't specify the return type because Swift is smart enough to infer the type from the statement that we have just written, X into X plus 2. And this is the closures. Some languages call it lambdas. So you might already be familiar with this. This is just a fancy way to do it. So when they're trailing closures, you can just pull them out of the method's bracket. And print the result, the value is still the same. Let's see another syntax for this. You don't even have to use the X variable out there. Swift has the shorthand names, $0, which refers to the first argument of the closure. If there are more than one, so $1. If there are two, $0, $1, $2, to refer to the first, second, and third argument of the closure. So the result is still going to be the same. So what exactly does the gradient function take? The gradient function over here takes an x, which is of type t. This is all generics. So in a function, which is differentiable, which takes t and returns a tensor. And we do have some generic constraints over there where t is differentiable. So the t, in our case, it was float. It is differentiable. And we'll get into TensorFlow floating point is just float, but for in tensor ways. So the most important thing of our entire session, TensorFlow. You might notice the capital T in TensorFlow. This is because we are no longer dealing in Python. This is Swift way of doing things. So TensorFlow is the Swift module, providing all the high-level Swift APIs. So tensor stands, tensor is a vector. And if you want a tensor of rank 2, you could combine two vectors. So vectors not only have magnitude, but they also have direction. So let's say you're at a railway station, you see the train going left, but the person on the other end will see the train going right. So vectors have a direction, a frame of reference. They have more information than a normal scalar. So tensors are a mathematical way of representing vectors, and tensors could contain one vector, or they could be of rank 2, they could be of rank 3, each time composing of multiple vectors. And flow is a bunch of operations that you perform on these tensors, hence the name TensorFlow. So let's consider a simplified magical formula, which is 2x plus 2. This is a linear equation. The graph is simple. And we're going to build a machine learning model. The model will help us predict the values that, So these are features. What exactly are features? Features are input to a model. So features are scalar. You see, they are an array of float. So we need tensors to work in TensorFlow. So we convert them to a tensor using the tensors, supply the shape and supply the scalar features. Then we already know the labels. Labels are the expected output. So we'll be using, if you've guessed it right, we'll be using supervised learning. And we'll be using these features and these labels, form training examples, and train a model. So we're taking features.map, magical formula. What map essentially does is goes through every element of the array, applies the function magical formula. That's it. And In a similar way, we convert the scalar labels to tensors. And you might notice the difference in feature set and label set, which is tensor, you have angle brackets, then you have float, and then you have tensor, no angle brackets. So what happened over here is Swift was able to infer the generic type. So you could just avoid supplying float and just call it tensor shape and just apply the scalars. And let's just print out all our features that we expect. So let's say for 2, we expect 6, 4, 10, 8, 18, 2x plus 2, so 2 into 2 plus 4 plus 2, 6. So 2 into 4 is 8 plus 2, that's 10. So 100, 2 into 100 is 200 plus 2, 202. So a model should be given a feature, a model should be able to predict the label. Emphasis on the word predict. A model will never give us a discrete answer. It will try to always predict a value. So we're going to use a very simple neural net. One input, one output, and a neuron in between. So this is a model. The way you define models in Swift is by conforming to the layer protocol. Layers essentially mean they're models. They could be hidden layers, they could be the output layer. So in this case, if you notice, we compose of existing models. So our magical model conforms to layers. And the layer protocol has a function called as function that we have to implement. So we go over here, go to neuron. So a neuron is simply a dense layer. Input size is 1, output size is 1. Obviously, it's a simple dense layer. So if you look at it, we're just composing of an existing dense layer. And the dense layer, they have weight, they have biases, which we'll observe at a later point of time. The dense itself is a layer. You see, we're building our layers, composing on top of other layers. Going back to this function, call as function, it's as illustrative as it can be. Call as function literally says, you can call this model as a function. So and this function has to be differentiable. So here, I'm creating a model object, and then I just supply. I can use, because we have implemented the call as function method, I can just apply the input to the model. And let's start training. So learning phase, we're setting it to training. So we're going to train a model. And learning phase is essentially an enum. Enum could be one of those values. It could either be in training phase or it could be in inference. Inference is when we start predicting those values. So right now, we are in training phase. So obviously, the values that a model will predict may or may not be accurate. So we need a way to measure the deviation from the expected value to the predicted value. And our end goal is to minimize the loss that we encounter over the entire training phase. So we use an optimizer, and we're using a simple, most commonly known Adam optimizer. We supply the model, and learning rate, we start with 0.1. Learning rate is a hyperparameter. So a hyperparameter is essentially what we tweak throughout the phase of our training. And the epoch count is 360. So epoch is essentially, one epoch essentially means the model has gone through all the examples, all the training examples, at least once. So we go to 360 epoch counts, and training loss, we'll just accumulate all the training loss and plot them out in the end to get a nice graph. This is just a configuration before we start training. So we're going from 1 to epoch count. This is essentially creating a range. It starts at 1, goes up to the epoch count, which in this case is 360. So 1, 2, 3, 4, 358, 359, 360. So for each of those epochs, again, I'm going to calculate the gradient. So the value with gradient takes a t, which is again differentiable. So in our case, a model is differentiable, and a function. And so we're going to compute the gradient. We supply the feature set to a model that gives us the prediction. And to compute how good our prediction is, we compute our losses using the mean squared error. So as the name is as descriptive as it could be. So you calculate the mean, you calculate the square of expected minus the predicted. And in the expected field, you supply the label set that we constructed earlier. Now, value with gradient returns a tuple. A tuple is essentially, it could be 2 values, it could be 3 values. So the 2 values over here, it returns a tensor of R and it returns a gradient. The value is the loss. So you're just going to store them in loss and gradient. And now using the optimizer, we're going to update a model along the gradient. You see how Swift API is very expressive. It's just like reading an English prose. So the optimizer has a function update that we're using. Interesting thing to note about here is mutating. It's being explicit that it's going to mutate. And in the cases where we need, so we spoke about value semantics. In the cases where we need the reference semantics, you could just apply in-out. In-out essentially means we're going to pass the pointer to this object. And along the direction, along is the name parameter, direction just gives. So this is another way to name your functions. So your arguments could have underscores, essentially you call them without any name, or they could have name arguments, or they could have name arguments, and the ones that you don't call. So using the optimizer, you're updating the model along the gradient. The way you supply an in-out variable is using the AND operator. So the AND followed by the object. So basically supplying the pointer along the gradient. And there it is. So if you notice how Swift lets you go from value semantics to reference semantics with you being explicit, the only way to get to reference semantics is by you specifying in-out in your method. And let's calculate the loss. So the loss, if you remember, was a tensor. So we move back to a scalar value. So this is the loss over the epoch. We'll append it to a training loss. And at random intervals, we'll just print it out, just for our sake. And this is the entire training phase. Let's see, at epoch 111, it's 0.1, epoch 112, 0.9, 126, 0.054. Ideally, it should go down as the number of epochs increase. And let's start. Now, these numbers don't make sense. Let's start plotting a graph. So TensorFlow, Swift for TensorFlow is still in beta. So there are certain features that are missing that may not be there, like something as powerful as a pie plot. So what do you do in that case? So Swift has great support to interact with Python. So Swift has great Python interoperability. So I can just import a module called Python, just configure my shell. I want my plotting to be done inline. And here I have imported matplotlib.pyplot. This PLT is essentially now Python is a dynamic language, no types. Swift has a type system. So how do these mappings happen? Swift has a protocol called Python convertible. or Python object protocol. I forgot the name, but uh, all Python objects conform to that protocol. So essentially, you can interact with any Python API that you'd like. And we're setting the figure size 16 by 12 inches. We're plotting the training loss. The x-axis is epoch, and the y-axis is loss. And we're just going to show our figure. That's a nice curve. You see, as the number of epoch goes from 0, 50, 100, 150, 200, 250 to 350, we want our losses to go down, and that seems to be happening. So training did go well. You could have probably stopped at an earlier epoch. Now let's go to the inference phase. Inference, if you remember, is an enum part of learning phase. We're telling a model we're going to start using it for prediction. And now I have these unlabeled data set 10, 20, 30. We're going to try to predict the value for 10, 20, 30, 40, 50, 60, 80, 100. And the unlabeled data set is a scalar. We're going to convert to a vector, to a tensor. The shape is 8 by 1 because 8 unlabeled data set could have been unlabeled.count and 1 output. Predictions. Now we use our trained model and send in our unlabeled data set. Now we know our expected values because it's a simple equation. We'll just do unlabeled.map magical formula and we get our expected values. And let's see how are we doing. So the predictive value was 21.993866 and the expected was 22. Close enough. I mean, at least my math teacher would approve. The prediction for 162.00154 expected 162. And our magical formula was 2x plus 2. If you remember, 2x plus 2 is a simple line, which is essentially y equal to mx plus c. But the most common terms used around machine learning would be y equal to wx plus b, where w being the weights and b being the bias. So essentially, what we want a machine learning model to predict is it should have accumulated a weight of 2 and a bias of 2. Let's see what our weights and biases are. So I'm just going to print my weight using the model's neurons weight and the model's neurons bias. The weight is 2.001097, close enough. Bias is 1.992768, close enough. Now let's look at the second example using Swift for TensorFlow. All of you might be familiar with this data set, MNIST. We're trying to recognize the handwritten digits over here. So for this example, we will just go to runtime. We're going to enable the GPU because there are tons of images and GPU boost would really help us. Swift has a dataset API like the Python one, but it's not as mature as the Python one, but we still have the MNIST dataset. So how do we get the MNIST dataset? So I'm setting an install location within the current working directory as Swift external. And I'm installing an external package that's hosted on GitHub. So it's github.com/tensorflow/Swift models. The branch is master, and I'm setting it as datasets. So I'm specifically interested in datasets. And let's see, this does take a while because it will go figure out the dependencies for that repo, get those. It does take a while. So let's say after a while, we got all the packages that we wanted, and we can verify that we have installed them by just going to the folder icon on the left. Swift external, and you see modules and packages that came over based on our cloning. And this uses Swift Package Manager. So you see Swift has a really good package manager entirely built out of Swift. That's amazing. And let's go back to our program. So a basic input, import TensorFlow, Python for plotting our graphs and a bunch of other stuff, matplotlib, we want pyplot for plotting our graphs. And in this case, we'll also get NumPy. So I just do python.import NumPy. Fun fact, NumPy, was it NumPy? Yeah, NumPy or Panda was one of these Python libraries for the highly efficient computations. They use C or C++, whereas in Swift, where the performance is comparable, you could entirely build a library and through have Swift as the stack. Okay, all our inputs are done. Let's move to the next phase, importing the datasets. So this is how we can access the Swift dataset API, get an MNIST. So the batch size, so obviously the MNIST dataset is huge. So you want to process in batches. So you just apply it to the MNIST, and this is the initializer for MNIST. It takes a batch size, which is 512 in our case. We don't really want to flatten. We'll get to what flattening is later on. Normalizing essentially helps to bring the values of the data set to an acceptable range. So if it's like 5,000 to 10,000, we could just get it back to an acceptable range. And MNIST has 6,000 training images that we can use. We're just going to print out a few images from the dataset, 66 to be precise. So this is the entirety of MNIST dataset, handwritten digits, still better than my handwriting, I guess. So we're going to define a model. Like previously, it conforms to layer. So in this case, we're going to have some hidden layer. So first is the flattened layer. So the images are of 28 by 28, and we want to flatten them into a single array. So you see the input size is 28 by 28. As we have flattened them, we have converted a two dimension to a single dimension. The output size of the hidden layer is 300, and the activation we're using is ReLU. So yeah, this, as I already said, the image width to image height is 28 by 28. So we're flattening them using the flattened layer. And then we're just computing the input size. The output size we're setting as 300. The activation is ReLU, rectified linear unit. Anything less than 0, like negative or 0, the answer is 0. Anything above 0, the answer increases. So it is a linear graph. And the output layer in our case is going to be a dense layer. Input size is 300, which is equal to the output size of the hidden layer. And then the output size of the output layer is 10 because we're going to classify digits 0 to 9. And the activation, input size 300, output size 10. And the activation that we're going to use is softmax. Softmax has been proven to be great for classification problems. So the output layer will be using softmax. And this again, call as function, since we are conforming to layer, we're going to implement call as function. Call function is not really a thing restricted to layer. You can have any of your structs implement call function, and you can just call those structs as a function after you create an object. So the caller function, it will be a sequence input layer. First, the input will go through the flattened layer, and obviously we can get rid of the return since it's a single line. So first it goes to flatten, then goes to the head layer, and then it goes to the output layer. And now we can just create a model object. In this case, we'll go with 10 epochs, optimize the add-in, the training accuracy results, and the train loss results. Yeah. So the epoch goes from 1 to epoch of count. It's a different way of writing. It's still the range. So we're defining the epoch loss. We're going to calculate the accuracy in this case, and then we have a batch count. The method is used, so I just omitted them out for brevity. So MNIST training data set, the training data set, you can sequentially access them. So there is a MNIST training. MNIST.training is of type batcher, and so the batch has an operation sequence wherein you can access your models. Yeah. So the batch. So you see the batch that we got from the sequence. Is of type tensor pair, and the tensor pair has two two variables, first and second, where first is my input feature. So I'm supplying that to the model like we did previously. I get logits. Logits are basically probabilities, a bunch of them, and then I'll supply that to soft cross entropy, and the labels, the expected labels are basically batch.second. So the tensor pair, the first contains the input, and the expected values is in the label. And as we're using softmax, we're going to use softmax cross entropy to calculate the loss. We supply the predictions. So softmax cross entropy will calculate the difference in probabilities with the predicted value and the expected value. Now, using the optimizer, we're going to update the model along the gradient. Now, I'm just calculating using the same logits over here. I'm going to calculate the accuracy for this. And logits are a bunch of probabilities. They're a huge array, so we're trying to find out what number is this maximum probable to. So we do logits.argmax, and we supply the truths as batch.second. And the accuracy function is essentially comparing the predictions are equal to truths, and we calculate the mean over how accurate has been. So we calculate the mean and then just convert it over to the scalar. So the new syntax over here is a dot and equal to. What this essentially is doing is, if you're familiar with broadcasting in Python, this essentially will compare all the elements of the predictions with the truths. And the truths being the labels and the prediction being what our model generated. So this supports broadcasting. It takes a tensor on the left-hand side, takes a tensor on the right. So we're comparing two tensors and whether those tensors are equal or not. And tensor, as I said, they could be huge vectors. And then using the accuracy, then we convert the loss from a tensor to a scalar quantity, and we just increment the batch count. And now these are just a bunch of equations. Epoch accuracy, we're just dividing by batch count. Epoch loss over the batch count. And then we just appending the results over to crane accuracy results, crane loss results, and just printing them out. And this is our entire training function over the epoch. Let's see how this works in action. So we have epoch 1, epoch 2, epoch 3, epoch 5, accuracy 0.99, 0.99, and 0.99. That's really great. So, and we're just going to do a simple plotting. We set the figure size. We said we're going to plot our accuracy, and we are going to plot our losses using PyPlot. And here we go. So you see our accuracy is increasing as the epoch count increases, and the losses are decreasing as our epoch count increases. That is great. That is what we actually wanted. So let's test this out on a test set. So you use the way you access it, access the test set is using mnest, the object that we created initially, and just test and sequence similar to how we get the batch out of the sequence. And this is the only change. In the case of training, we were accessing it using mnest.training. And then we get the predictions. We get the logics, and then we figure out predictions using logics.rmax squeezing axis one, essentially saying like give us the value with the highest probability. Let's just print it out. So the test batch accuracy seems to be going great. Okay, and let's see. If you look at this, our example 0 was prediction was 4, the actual value was 4. At example 13, example 14, example 15 is where we screwed up. The prediction was 1, but the actual value was 7. But we did achieve a high enough accuracy. So let's see. Oops. Oh. Yeah, that's about it. I am on Twitter. I'm on Medium. I'm planning to upload. I have created a repo on GitHub. I just haven't uploaded all the code yet. I'll just clean up my code and upload it over there. Well, thank you, everyone. What we can look at the 7 that we failed to uh, decode. Just I do have the code. Um, here. Okay. Uh, so this is the 7 we our model decoded as 1. I mean, that's okay-ish. Well, and you might realize like Swift for TensorFlow is still in beta, so there's still many missing aspects, and the API is still in flux. Like the example that we used here might not be valid in a few months. So, well, that's it for today. Thank you everyone for joining in the session. The code again